So here 1 is less than 4. So this is the lowest cost. So it start moving from S node to A node. And that is the first movement. The goal node is available, is found in this level 2. It will be come out of this and it say that the algorithm is exit from that point. Space complexity we referred with the order of B plus C star slash sigma. Dear students, welcome to computer science classes. I am Ravi Kumar KR, lecturer in computer science, Vidhyaashram First Grade College, Temple of Excellence, MYSURU. Students, let us start our discussion with the chapter Problem Solving by Searching. So in this session, we are going to cover the topics Uniform Cost Search Algorithm, Iterative Deepening Depth First Search, and Bidirectional Search Algorithm. These are topics to be covered in this session. Now let us start with the first one, Uniform Cost Search. It is a type of algorithm. Now let us see the definition of this. So it is a searching algorithm used for traversing a weighted tree or a graph. So we are going to implement this through a tree or a graph. It is a non-linear data structure. So it is used for traversing. Traversing means visiting all the nodes in a data structure. So it comes into play when a different cost is available for each edge. As all of you know that, and each edge of a tree or a graph will be having its a cost value, or the value that is called a cost value. If the values are different, then we are able to apply this uniform cost search algorithm. Now the primary goal of this is to find a path to the goal node which has the lowest cumulative cost. So it is going to prefer or is going to move to the node where it has the lowest cumulative cost. And it used to solve a graph or tree where the optimal cost is in demand. Now this algorithm is implemented by a priority queue. So it gives the maximum priority to the lowest cumulative cost. So as we know that this uniform cost search algorithm is going to work with the cost for the each edge, and this edge is going to give priority to the nodes which has the lowest cumulative cost. So this is the definition of uniform cost search. Now let's see the example for this. Now look at the example here. So this is a tree structure, and here these are the different nodes S, A, B, E, G, F, D, G, B, and G. These are the different nodes of a tree, and S is the starting, that is the root node. Now there are, if you look at the level here, so this is called level 0, level 1, 2, 3, and 4. There are 4 levels in this tree or a graph. Now in this algorithm is going to start with the starting node, that is the root node. From here, and if you compare, there are 2 nodes here. So one is A and B. Now this is called the nodes, and these are the cost value or the cost. So if you compare this here, the cost value for A is 1, and here cost value for B node is 4. So here 1 is less than 4. So this is the lowest cost. So it start moving from S node to A node. And that is the first movement. So after this, again there are 2 nodes for this here. One is 3, that is B, cost value is 3, and D, the cost value is 2. So here 2 is lesser than 3. It has the lowest cost. So it takes the next movement from A to D. That is the second one. Next one is, if you look at the next movement, G is the goal node. G is the goal node. So from here directly it takes the next node, that is G. So in that way, if you look into that, the goal node is G. So it starts moving from searching from the root or the starting node. From here S to A, the cost is 1, and A to D, the uniform cost value is 2 and from here it is 3. So by following or by moving to the node which has the lowest cost value, so finally is going to reach the goal node. So this is how the uniform cost search algorithm works. In the next slide, we will see what are the different components of this, or what about the completeness. So here, whether the algorithm is to complete or not, yes, if there is a solution, you say it will find it. So the meaning here is, if you look at the previous example, so if it is not able to find the goal node, for example, either it takes this one or this route, any of the route or any of the node, but here, if the goal node is not available or it is not able to reach the goal node, then it is incomplete. That is the first point. Next one is time complexity. So we are going to calculate the worst case time for this algorithm, and complexity of uniform cost search is, this is order of B plus C star oblique sigma and close the bracket. So this is nothing but your complexity of uniform search, the order of B. What is the space complexity? Space complexity we referred with the order of B plus C star slash sigma. So here in this example, the complexity of uniform cost plus space complexity are almost same. So this is uniform cost search algorithm. Now let us see the advantage of this. So here it is optimal because at every state the path with the least count is chosen. So it is preferable or it is optimal because it's going to always select the least cost of the edge. What's the drawback of this? Disadvantages? It does not care about number of steps involved in searching and only concerned about the path cost. Due to this, the algorithm may be stuck in an infinite loop. So this is the main drawback of this, as it depending on or is going to work or is going to concern only the value, cost value or the path cost. So it may not consider the number of steps taken to reach the goal node. So that's the main drawback of this. So it may leads to the infinite loop. So this is the drawback or disadvantage of uniform cost search algorithm. Now in the next slide, we will see another type of algorithm, iterative deepening depth first search. It is another type of algorithm. Now let us see the definition of this. So it is an algorithm, it is a combination of DFS and BFS algorithm. So it finds out the best depth limit and does it by gradually increasing the limit until a goal is found. So here, this algorithm performs depth first search up to certain depth limit and keeps increasing the depth limit after each iteration until the goal node is found. So it is going to first is going to work with perform DFS up to certain limit, then it's going to increase the iteration, is going to increase the limit after if the goal node is not found. Next one is this algorithm combines the benefits of breadth first search. This is breadth first search and the depth first search algorithm. So here this is what is the advantage of this. So it is going to work or is going to consider the best benefits of DFS and benefits of BFS. So based on that is going to work. Next, the iterative search algorithm is useful uniform search when search space is large and depth of the goal node is unknown. So what is the advantage of this? The one point is that so it is very, very optimal, is very useful where there is a large space or where there is a large number of nodes and depth of the goal is unknown. So this is the definition of iterative deepening depth first search. Now let's see the example here. Now look at the example here. So this is the graph S, B, E, S, F, K, G, D, I, H. All these are different nodes of a graph here. So this is level 0, level 1, and level 2, and level 3. So what is the meaning of deepening depth first search algorithm? So here, so this is, for example, this is G is the goal node. G is the goal node. So when you want to search for this, so at the level 0, this is the starting point or the route from where it starts searching for the goal node. So here, so this is level 0, it is not a goal node. Then it is going to increase the limit. So it's going to the limit level 1. So it's going to next level. So in the next level, we have B as well as S, that is level 2. So if the goal node is available, is found in this level 2, it will be come out of this and it say that the algorithm is exit from that point. Suppose the goal node is not found even at the level 1, it increase the limit to level 2. So here, once the level 2, in this level, goal node is available or it is there, so it's going to reach the goal. So that is the definition of iterative deepening depth first search. See, that is what we have seen the definition here. It performed depth first search up to certain limit. That's what we have seen here. Suppose it keeps increasing the limit, increasing the depth first, until the goal node is found. That is the meaning of this here. If the goal node is not found in level 0, it extends the limit to level 1, then it will do the search operation. And if the goal node is not found here, it increases the limit to next level so that it's going to proceed till it reaches the goal node. So this is the iterative deepening depth first search algorithm. Now let us see what is the working of this here. In the first iteration is A, means in the first iteration, the start node is A, root node, so it's going to enter in the level 0. This is a level 1. Next iteration is, there are B and C. So in the next iteration, in the next level, we have B and C. So it is A, B, C. So this is traversing to different nodes. This is level 1. In the next iteration, it goes to level 3 here, 0, 1, 2. In level 2, we find that D, E, F, and G. So it is going to traverse. In this first one is A, B, D, E, C, F, G. Here, A, B, D. From here, we have go to this level here. So D, and again here backtracking. After backtracking, come to E. After this, again from backtracking here, from backtracking to S, then comes to C, C to F, and again F backtracking to C, and next to G. So this is the traversing in third iteration. Iterative deepening depth first search, that is the meaning of this. So in second level, it is third iteration. Now look at the next level, that is level 3. So we will be having another level, different nodes here. So how is it going to traverse? From here, start with A, B, D, and next level is H. Again H, going backtracking to I, backtracking B, B to E, backtracking S, again to C, C to F, F to K, and again backtracking here. So F to S, backtracking, and S to G. So, and after G. So this is how the next iteration. So in the final iteration, you can see all these things, and G is the goal node. So this is how the iterative deepening depth first search algorithm works. So it is going to increase the limit or increase the levels if the goal node is not found within the prescribed or within the defined limit. In the next slide, we will see about the completeness and other factors. Completeness, it is if the branching factor is finite, means if the limit is defined is a finite value, then we say it is a complete. So it's a completeness. Next one, time complexity. So time complexity we represent with the order of B and D. So here B is the branching factor, means nothing but the number of limitations. So and D is the depth. So this is, so here B is the branching factor, limit as well as depth. So this is order of BD. This is time complexity, and space complexity is also will be order of O here, nothing but order of B and D. Now optimal, if you say is optimal or not, so it is optimal if the path cost is non-decreasing function of the depth of the node. So only if it is optimal if the path cost should not be decreasing. So these are all the factors to say about the iterative deepening depth first search algorithm. Now we move on to next algorithm, that is bidirectional search algorithm. Bidirectional search algorithm. Now let us see the definition of this. In bidirectional search algorithm, it runs two simultaneous searches, one from the initial state called as a forward search and other from the goal node called as a backward search to find the goal node. So the bidirectional, as the name itself says, so it is going to search for the goal node on two simultaneous directions, one from the starting at the initial node called a starting point from the start node, and another from the, it is called a backward search from the goal node. So that's why it is called as bidirectional search algorithm. So it replaces one single search graph with two small subgraphs in which one starts the search from the initial vertex, other from the goal vertex. Means because of this, so entire graph will be divided into two subgraphs. Then one start from the beginning and in another start from the goal vertex. Now the search stops when these two graphs intersects each other, because this is going to divide the given graph into two subgraph or two subsets. So when they are going to intersect, at that point is going to stop searching for the goal node. Now it can use search techniques such as BFS and DFS and DLS. Already we have seen the definition and explanation of all these search. So it is also a combination, or it is going to make use of these different techniques used in all these types of algorithm. So it is a bidirectional search algorithm. Now let us see the diagram here. So this is a graph here. So as we have seen that this is the node 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 13, 14, 15, 12 and 16. These are all the different nodes, and this is the root node starting value, and this is comparative testing. See here this is called, a line is called intersection node, 9 is an intersection node, and this is the goal node here. So goal node. So here as you see the diagram here, so this entire graph is divided into two subsets. So this is the one part of it, and this is another part of the given graph. So here as per the definition, so the search algorithm starts simultaneously from this root node for one subset, and another start from the goal node. This is another subset. So while in searching for the goal node, so this is the intersection node where the search operation stops here. So it's going to from here start from the search from the root node and moving towards the goal node, and here in the another subset it starts searching from the goal node and moving towards the root node. So at particular of time or at particular stage they are going to intersect at this point. So this is called as intersection node. So at this stage the algorithm stops functioning or stops working. So this is the definition of bidirectional search algorithm. Now let us see the different factors for this. So here one is completeness. So it is complete if we use BFS in both search. We are using that, then it is complete. Then what is the time complexity? It is again order of B and D. And even space complexity we represent with order of B, D. And optimal, it is optimal. So optimal means it is definitely is going to find the goal is within the limit or within the graph. These are the points about bidirectional search algorithm. Students, so far we have discussed about another 3 types of algorithms or search algorithm. Now let us continue our discussion in my next session. Thank you very much.